Right. Okay. Understand. Right. So, yeah, thank you for coming for my talk about SatNav. What I'm going to do is just talk a little bit about myself before I go into the meat of the talk. I studied for a PhD at Jodrell Bank. Well, now nearly 40 years ago, I started my studies. Thesis was on H1 observations of groups of galaxies. And after completing my thesis, I didn't have an academic career. I worked in IT pretty much for my whole working life. I took early retirement in April 2018. But while I was in my last 4 years of my job, winding down to retirement, I started a popular science blog. Only intended to do it for a few months, and then I thought, oh, I'll get bored with this. But I found that I was enjoying it more than the day job, and it's just kept going, and it now has about 2,500 followers. So it's explainingscience.org. So this is what I'm going to talk about in this talk. I'm going to give a brief history of SatNav. I'm going to talk about how it works at a fairly high level. I'm going to talk a bit about the astronomical impacts of SatNav satellites, both radio and optical observations. I'm going to talk about the limits to accuracy of SatNav systems and the ways these can be augmented when you need very high accuracy. I'm going to talk a bit about the SatNav systems we use today and the ones that might be coming along in the future. And finally, I'm going to talk about something that I think will be more important in the future and more of a threat: jamming SatNav, preventing users from receiving SatNav signals. So let's start with introduction. Right, SatNav is an essential part of our daily life. You know, everything from directing our holiday aeroplanes to enabling us to drive around an unfamiliar city with something like Google Maps. Most cars today now have an inbuilt SatNav system. You can buy very accurate handheld GPS units at a very reasonable price. And you can even buy little GPS trackers to track your kids, to know their whereabouts, or even your pets at a very modest price. And I, for one, I'm totally reliant on this technology using Google Maps because it tells you not only where you need to go, but where you are at the moment. In fact, nowadays, nearly half the world's population has a SatNav system in their pocket in the way of a smartphone. So let's talk a little bit about timelines. Now, the terms GPS and SatNav are often used interchangeably, but there's actually, as I'll say later, there's actually 4 different global SatNav systems in use today. And GPS, which stands for Global Positioning System, was the first one, and it's operated by the US government. But others have come along there. But even so, people still use GPS and SatNav as meaning the same thing, but they're not. So a little bit about the timeline. The first ever GPS satellite was launched in 1978, and by the mid-80s, it was up to 10. GPS was always intended to be a military system, but things changed a little bit in 1983, when some of you may remember a South Korean aircraft was shot down after it had accidentally strayed into Soviet airspace. And accident investigations determined that the plane's navigation systems had failed. This was in the middle of the Cold War, and there's a heightened tension between the Soviet Union and the American bloc. And the Soviets had shot down what they deemed to be a hostile aircraft straying onto their airspace. So the same year, Ronald Reagan signed an executive order to try and prevent things like this happening. And he declared that when the system was complete, it would be civilians will be able to use this system as well as the military. It would be a dual purpose system. And this headline here isn't actually quite right, because a little bit misleading, because what Reagan did was he allowed access to GPS, but it had a fuzzy access. Access was deliberately reduced so that civilian users would only be able to determine the position to about 100 meters. Only the military would access to high precision GPS. And it was another president who finished the job. Another key thing, early history, was in 1991, First Gulf War, America and its allies against Iraq. GPS was widely used by troops on the ground and by missiles in that war. It really came into its own. The same year, we had our first lightweight GPS receiver. And I find this quite amusing, actually. Lightweight, 1.25 kilos, about the weight of a bag of sugar, when you think about how light a GPS receiver is nowadays. Another milestone was in 1993, when GPS had complete coverage of the Earth's surface. And you need 24 satellites to do this, well, I'll explain later. In 1996, Bill Clinton made an announcement called something called selective availability will be switched off by the year 2000. And what selective availability is it adds intentional errors of about 100 meters to the publicly available navigational signals. And these are what we call pseudo-random errors. They're generated by a cryptographic algorithm from a classified seed key only available to authorized users with the receiver. Right? And the authorized user would be the US military, its allies, and a few other users, mostly in the US government. So even if you have the receiver, it wasn't enough, and you needed to also have the key, which changed daily. So in 1996, Bill Clinton says this is going to be switched off, change of policy. And in 2000, this happened. So GPS was fully available for civilian use. Selective availability was turned off. And now we're in the position where a little over 20 years later, where satellite nav systems are an indispensable part of day-to-day life. So I'm going to go on now, unless there's any pressing questions, about how sat-nav systems work. I'm going to talk about GPS, but all sat-nav systems work the same way. So GPS is a network of satellites in orbit around the Earth. In total, since 1978, the US has launched 75 GPS satellites. And these satellites are in middle Earth orbit, roughly halfway between low Earth orbit satellites at the International Space Station and the higher geostationary orbits used by satellites which transmit TV signals. Now, since the first launch, there's been a couple of launch failures, and these satellites have a lifetime of about 12 to 15 years. So although 75 have been launched, there's only 31 working at the moment, and no satellites launched before 1997 are working. The satellites aren't in the same orbit. They are all at the same distance from the Earth's surface, 20,200 kilometers, but the orbits are in 6 different orbital planes with 4 satellites in each orbital plane, as you can see in this diagram. And this diagram shows the latest satellites, and it's over time these have been improved. The first satellites were called Block 1. The latest ones, which were launched in 2018, are just called Block 3A. 4 of these have been launched, another 6 have been ordered. And these have things like increased power, and they also have something called laser retroflectors, which allow trackings of the orbits of the satellites independent of the radio signals. So improved position information. So if we look at each satellite as it moves through its orbit, It appears to an observer on the Earth to rise, move slowly through the sky, then set a few hours later. So because there are 31 satellites in orbit, from a given point on the Earth, there'll be 7 or 8 visible at a given time. And as I'm going to explain next, you only actually need a good signal from 4 satellites to get next accurate position. So this is just going to be an overview of how it works. You know, there's not going to be detail of the individual messages, but I'll talk about the components in the satellite messages. So each GPS satellite has a set of atomic clocks, and these are accurate to a few billionths of a second a day. And these stock clocks are kept in step with the atomic clocks on the ground. The satellites, so all the GPS satellites should show the same time. The satellites have a transmitter which sends a signal to Earth, and the power is roughly 0.5 kilowatt. So that's roughly similar to the power radiated by the transmitter on a mobile phone mast. The 3 parts to the signal, logically has 3 components: which satellite is sending it, when it was sent to a very high accuracy, and the position of the satellite. So this enables the receiver to know where the signal is coming from. So when the GPS receiver receives the signal, it can compare the time in which it received the signal with the time it was transmitted, and thus work out how long the signal has taken to travel. And it's quite simple. You know, the distance between the receiver and the satellite is equal to the time difference times the speed of light. So if we had a signal which took exactly 0.1 seconds to reach us, then the satellite must be 30,000, just under 30,000 kilometers away. The speed of light being just under 300,000 kilometers a second. So what this tells us is it doesn't actually tell you where the satellite is. All it tells you is that you are on a point, a given location from a satellite. So let's take an example. We worked out the distance from the satellite as 25,000 kilometers. Then all that was tell us, you know, that we are somewhere on a surface of a sphere of points 25,000 kilometers from satellite A. If we add a second signal, so we could, for instance, from the second signal we picked up, we would know that, let's say we're 35,000 kilometers from satellite B, then our location would be anywhere on a ring where the 2 spheres intersect. And if we add a third sphere, then it narrows it down to 2 possible locations where all 3 spheres intersect. In general, if 3 spheres intersect, they'll intersect at 2 places. But as you can see, in one of those places is it won't be on the surface of the Earth. Only one of those will be a sensible location. In this case, it's location Y. However, that's not the full story, because this only works if the GPS receiver has a super accurate atomic clock which is perfectly synchronized with the GPS satellites. And that's clearly not that's not the case. You know, the clock on your mobile phone is going to be out a fraction of a second with the super accurate atomic clocks. And that accuracy is probably not even going to be constant. So what you need to do then is to work out TC. So we'll just call this the time correction. It's a difference between the time on the GPS receiver and the time on the satellite clock. And in order to do this, it's actually quite simple. You need a signal from a 4th satellite, and then you can solve the equations then to work out the X, Y, Z coordinates of the satellite and the time correction TC. And for people more mathematically inclined, I've put the GPS equations there on the bottom of my post if anybody wants to check those up. Right. Now, there are two other really interesting things. Remember, the atomic clocks are super accurate and they're not on the surface of the Earth. And the first thing you may know is that Einstein's theory of special relativity tells us that moving clocks run slow. The clocks on the satellites, which are orbiting at 14,000 kilometers an hour, according to special relativity, would run more slowly than a clock located at the Earth's surface. And this is the time dilation formula there. Okay. But there's another effect as well, because there's general relativity tells us that an object in a gravitational field time is dilated. Now, on the surface of the Earth, the gravitational field due to the Earth is stronger than at 22,000 to 20,200 kilometers above the surface of the Earth. So in this case, the satellite clocks would run faster at this location from the Earth, well above the Earth's surface. And I put the formula there. Basically, the larger R, the less the time dilation, faster the clocks run. So if we combine these two effects, we've found that special relativity would cause the clocks to run more slowly at a very small rate. We're talking about 7.21 microseconds a day than at the Earth's surface. And general relativity would cause the clocks to run faster, 45.85 microseconds per day than at the Earth's surface. So when we combine these two effects, it means that the clocks on the satellite actually run slightly faster than they do at the Earth's surface. And what that means is that we've actually got to slow the clocks down slightly to bring them in step with the atomic clocks on the ground. The other thing you may want to know is when we talk about position of the satellite, what do we mean? Satellite positions are often expressed in what we call geocentric equatorial coordinates. So that's a similar XYZ coordinate system, but in this case, the origin is the center of the Earth. The x-axis is the point of the vernal equinox, zero right ascension. The z-axis is the north celestial pole, and the y-axis is at 90 degrees to the x-axis along the celestial equator. So what I'm going to do now is I'm just going to pause. Has anybody got any questions, or do we want to go straight on to the next bit?
I'm with you. I'm not sure if anyone else wants to ask a question now. It's okay. Important points. Does anyone want to join in?
Okay.
I'll carry on then, Steve.
Okay, right, we'll carry on. Right, so what I'm going to talk about now is the implications for astronomical observations. Now, okay, so I'm going to talk about, firstly, optical implications. Now, I'm just going to talk about some satellites in general. Sputnik 1 was the first satellite launched, as most people know, back in 1957. It had a magnitude of about 5, so it was visible to the naked eye as a faint object, orbited in a very elliptical orbit, this number being so low that it was slowed down by atmospheric drag each time, and after a few months returned to Earth. The International Space Station is probably the brightest object in the sky at the moment, and it's about minus 4.5, so comparable to Venus. Sometimes it even gets a bit brighter. So it's pretty bright, the International Space Station. So what's this object, you may ask? Now, these satellites were communication satellites, and they had 3 polished antennas about the size of a door, And occasionally one of these highly polished antennas would reflect sunlight directly down at Earth, and it created a predictable and quickly illuminated spot of light rushing on the Earth. And if you were on the ground looking at one of these, you'd see this bright flash, which would only last a few seconds, and these could go right up to -9. And these are so bright they could be seen in daytime. However, these satellites were all deorbited by the end of 2019. Now, other satellites you might have heard of is SpaceX Starlink satellites and the long satellite trains, because these are launched in batches of 60, and there have been many people have seen these stringing out along the night sky. But when these are in position, they're actually not particularly bright. They're round, and these are going to be in various orbits, probably about -6. So, sorry, but 6 magnitude. They're just about visible to the naked eye. GPS satellites, even better. There's because they're in such a high orbit, and also they're quite small. They're talking about minus magnitude of 11 to 12, so they're barely visible. So, implication on optical observing. I mean, if you're an astrophotographer with long exposure times, then you will pick them up. But compared to these other objects, like limited, it's these objects. These are going to be the biggies, because although they're not bright, there's a lot of them, and by the middle of the decade, there could be 12,000 of these in orbit. So these are the ones that are really upsetting astronomers. So what about radio astronomy? Well, these satellites transmit on frequencies between the 1 to 2 gigahertz range. For example, GPS satellites use a couple of frequencies in what we call the L bands, and I've put those there. And the reason for these frequencies is they easily pass through rain, storm, fog, and a reasonable amount of vegetation, which other frequencies might not do. But nobody should be doing radio astronomy at these frequencies. Radio astronomy takes place generally in particular bands which are protected. You're not allowed to transmit in them. For example, the 21 centimeter hydrogen line is this frequency, just over 1.42 gigs is the frequency of the line, but the protected band goes a good way either side of that. And there's another band in that range. And another one is the OH band, again, 1.66 gigs. And there are a few more protected bands in this range. So shouldn't really be any impact on radio astronomy. So I'm going to ask any more questions, or shall I carry on?
Yes, can I ask a question, Steve? It's
Shall I? I can't see who's speaking, so shall I do a gallery view?
It's Cos is speaking.
Yeah.
Oh, right. Hi, Cos. Right.
Hi, Steve. Thank you. I'm just astonished by connecting up what you said about the frequencies to the power output of a satellite.
Yeah.
So you said it was half a watt.
No. I'm going to talk about the power output of these. It's half a kilowatt. The GPS satellites are roughly the same power as a mobile phone mast, so it's about half a kilowatt.
So when we receive it on Earth, can I just ask a very elementary question? A phone, a smartphone, not only does it have a mobile detector
that
I hold in my hand, it's got a GPS receiver in it.
Yes.
Okay, I've heard it from the horse's mouth now.
Yeah, and it's at a different frequency than the mobile phone, yes, than
Yeah.
the phone lines. Yeah.
Okay, so I'm just getting my head around the fact that these phones that which we just dispose and throw away casually, blah blah blah. Um, by the time the signal receives, comes down to the palm of your hand, it's been so attenuated. I'm going, wow, oh my, OMG.
Yes. Mm.
Okay,
Yeah, I'll talk a little bit that later. The GPS signal you get is incredibly weak. You know, when by the time, you know, if you worked out, I mean, in intensity is power per unit area, and I'll talk about that later on in my talk. But the intensity of a GPS signal is incredibly weak by the time it gets to, because the transmitters are a long way away and the signal's not that strong to start with.
yeah, okay, thanks. If in your researches you could just post up a picture of an exploded view of the internal workings of a smartphone,
Yeah.
I'm sure I've got more capacity to go, oh my, OMG,
Mm.
see which bits are doing
Yeah.
what. Okay, thank you.
Right. Okay. Any more questions, or shall I go on? Okay.
I think carry on, please, Steve.
Right. Okay. I'll carry on. Right. So, whoops. So, what I'm going to do now is we've talked about GPS satellites. I mean, I'm going to talk about the limitations, some of the limitations we have with GPS. Now, one of them is the speed of radio waves isn't constant. As conditions in the upper atmosphere, known as the ionosphere, can cause these signals to slow down slightly. This makes the time taken for the signal to arrive at the receiver slightly longer, implying the satellite is further away than it actually is. Another factor is that large objects such as trees between the receiver and the GPS satellite may weaken the signal, and could, you know, if it was a very, very thick forest, block it altogether. A mitigation to the delay in the ionosphere is that the newer satellites transmit on multiple frequencies. So you can actually, the delay was slightly different from each frequency. You can actually work out the total delay by extrapolating the change in delay over the frequencies. Another sort of error is what we call multipath errors. These are generated when a GPS signal is reflected off tall buildings. And I've illustrated it here. You've got a receiver, let's say it's in a car, receives two signals from the same satellite. You've got direct signal, which is the yellow line, and reflected signal, which is the pink line. And the receiver might lock on to the wrong signal, and it can result in an incorrect distance if the wrong signal is chosen, or possibly even the two signals could interfere, cancel each other out. It's also possibility of errors caused by slight inaccuracies in the atomic clocks on the satellite, or even the satellite not knowing, wrongly calculating its own position. So this slide, which is taken from an official US government presentation, gives us some idea of the sort of errors we're talking about. Okay. And you can see that delay in the ionosphere is the biggest. There are things like receiver noise. The troposphere is the lower part of the atmosphere. It's quite small. Errors in its position is thought to be quite small. Clock errors would be bigger. So this is taken from this government information pack. But even if we take all these into account, GPS can provide an accuracy to within 10 meters, and normally considerably better than that. But it won't work if you've got even a building with very thick concrete walls. Signals won't get through, and it won't work underground either. And the other thing, of course, is that we're reliant on America, and I'll come on to this when I talk about other sat-nav systems. I think over the next 5 to 10 years, probably a lot longer, well, hopefully a lot longer, the US government will continue to operate and fund GPS as a free civilian service for the whole world to use. However, they still have the ability to deny use to a hostile country should the need ever arise. And one way they could do this is they could just switch off the satellite's transmitter when they pass over particular areas of the world. And the other thing to bear in mind is the US taxpayer stumps up roughly £1 billion a year to keep this running. And this is a combination of the operating costs and, you know, the satellites themselves have a lifetime of, say, 12 years, so they need to be replaced on a rolling basis. Although that might appear to be a large amount of money, if you divide that with by the population of America, which is roughly 1/3 of a billion, you're talking about $3 a head. So it's not a huge amount of money. So what I'm going to do now is I'm going to talk about augmentation. We've talked about GPS giving accuracy of 10 meters, hopefully better. But there are ways to augment this signal. There's a number of ways, but a common one is to use GPS to measure the position of objects where you already know their position. And if those are spaced out on a grid, then you can compare GPS position with real position and then use that known error to give you a more accurate position. So what I'm going to do is I'm just going to stop sharing for a minute and I'm going to share a little video clip I want to share. I need to share screen, but I'm going to share this now. So can you see my browser?
Not at the moment, Steve.
Right, I'll try now. Oh, you should do. And share screen. Oh, yeah, I know what I've done. I have to hit the share button now. Now, can you?
Yes.
Right.
Yeah.
So I'm going to show this little clip, which is from. It's one of the ways to augment a GPS signal to get better accuracy, and this is used by American aircraft. So there's no soundtrack, but I'm just going to play it and I'll give you some idea how it works. I'll talk. So you've got the reference stations spread throughout American airspace, and these are measuring position from GPS satellites. Send them to master stations. And these are uplinked then to geostationary satellites. And the GPS signals are augmented by the satellite, the position errors provided by the geostationary satellites. So that will give you greatly improved accuracy compared to standard GPS. Now, does anybody want to see that again, or was that self-explanatory?
Well, I'd like to see that again, please.
Right. Okay. Let's do it. Right. So we'll see it once more.
The yellow ones are the master stations, are they?
Yes. Yes. Yeah. If we look carefully.
And
So
these are sending messages back to the GPS satellites via the geostationary satellites.
no, the receiver gets two messages, one from the GPS satellites and one from the geostationary satellites. And you'll see that in the aircraft is receiving both messages. So the aircraft has a better GPS receiver than you'd have in your mobile phone.
We hope so.
Yeah. So whereas, you know, your mobile phone's good to 10 meters, right? You'll see this. I'll stop it when the aircraft is flying. You can see that's, I'm going to stop it now. So the aircraft is getting its GPS signals from GPS satellites, but it's also getting a correction message. So the aircraft's GPS is a much higher spec than you've got in your mobile phone, and it will get the correction messages and then be able to interpret its, you know, position to a fraction. You know, you're talking about order of centimeters rather than meters. And the military will use similar sorts of techniques. And this is just one way. There's also ways of doing it with ground stations as well. So
Can you just explain what your green line is?
That's a good question. I'm not sure. I'll tell you what, I'll show it once more and then we'll.
It's a green line, just the path of the aircraft.
Yeah, I think the green line is just past it. So if we watch it carefully, we've got our reference stations all have known position, right?
Are they emitting like, or are they all emitting like that example that's shown?
No, these are receiving information from GPS satellites. The GPS satellites are telling them their position, but these points know their own position, if you see what I mean. So if we go back, let me just go back a bit. Interesting this. So let's go back to here. So this one here, it's got a signal from GPS satellites and it's working out its position, but it already knows its position, you see, to a very, very high accuracy, right? Okay. So what it's doing is it's saying GPS tells me I'm X in position X, but I know I'm position Y, so I need to know the offsets. And these offsets will be due to things like conditions of the ionosphere, errors in the satellite clocks. So these will be the same in the whole area around that satellite, around that location. So what it's doing is saying, this is the error for this location. And it will be similar in nearby locations. And then it's telling these yellow blobs, the master stations, and I'm not sure why you need three. I mean, I would assume one would be enough, but it's just illustrated. I mean, it gives a bit of redundancy, I suppose, flying aircraft. So all these stations here are telling this master station, aha, GPS is wrong. If you use GPS, you're going to be out by 5.7 meters from, you know, at this location, or 8.3 meters at this location, etc. So this is all being collected in these master stations. And then they're sent up to these geostationary satellites, which you can't see there because these are much higher. You know, these because they're geostationary, they remain fixed above the United States. Okay. And then when our plane, so this information is sent up. Okay, so we've got our geostationary satellites. We stop here. So we've got our constellation of our 31 GPS satellites going around the Earth. And we've got our geostationary satellites, which is not quite to scale, but these are twice far away from the Earth, roughly, than the GPS satellites. In fact, they're not quite twice away. So these are actually fixed points in the sky because they're geostationary. So when our aircraft comes along, as we'll see next, right, it's got its GPS signals, but it's also got its correction messages from the geostationary satellites. So it's able to do something clever. Yeah. Aircraft uses GPS and WAAS. I can't remember what WAAS stands for. And the combination of the GPS signals and this, which gives the known error in GPS signals, which gives a very accurate position of the aircraft. So I'll stop this now. So are there any questions at this point?
WAS is the Wide Area Augmented Service, and it's part of the FAA and Department of Transport to provide that.
Sorry, who said that? Thank you.
Kevin.
Kevin.
Oh, hi, Kevin. Right, thank you. Right. No, that answers the question. Yeah, I did know that, but I'd forgotten. Right.
Yeah, I know.
Yeah, but it's pretty nifty idea. But without that, GPS wouldn't really probably be accurate enough if you're landing a plane. Okay.
Is this correction applied worldwide, or is it something particular to the States?
Well, this particular one is only to the States, but there are equivalent ones in other areas of the world, because those geostationary satellites are only over America.
Mm-hmm.
But there are other similar sort of things which apply to the whole world.
So the Galileo, which is the European equivalent of GPS, has got its Euro Geostationary Navigation Overlay Service. Obviously, much more catchy than EGNOS.
Yeah.
Thank you, Steve.
Okay. All right.
Perhaps the green is just the path of the aircraft.
Yeah, I think so. Right. So I'm going to go on to the next part of my talk.
The green was the track of the aircraft through the air.
Hmm.
It was just indicating the direction of travel.
You'd think actually that 10 meters would be not so relevant for an aeroplane when it's landing on a huge runway than for people trying to drive along which road they need to turn right down.
Yeah, I mean it's quite interesting, but then we've all seen this where GPS on our phone says we're somewhere, but we're actually not in that place. We're sort of across the road or something.
Yeah.
I think GPS is remarkably accurate when you're driving down the motorway. It almost knows which lane you're in, and as often as not is correct.
Mm.
I think mine is pretty old.
Maybe your driving's just erratic, Caroline.
But it says turn right, and you think, hang on a minute, does it mean this one or that one? It's the voice.
Yeah.
I think it's the voice.
It's the voice, isn't it? Yeah.
Yes.
But also, the older the GPS is, the more prone they were to navigational computational error. So the very early GPSs were only good to about 100 meters. And over the last sort of 5-10 years, as Steve was saying, that's come down to about 10 meters for a general purpose GPS receiver. And as you go up the product stack, you then get these augmented features which bring those extra signals in to improve the accuracy. So to get the WAS, you'd normally be looking at an aviation GPS unit.
Oh,
and they tend to start at thousands of pounds and go upwards.
Though presumably there's nothing stopping, you could buy an aviation GPS unit if you wanted to. I'm not sure if the purchase is restricted.
Yeah, you can buy aviation GPS units. That's no problem, because you buy them off over the counter and then mount them in your aircraft.
Yeah.
I think certain government agencies might be checking up on why you want them.
Possibly, yes.
You'd like to think so.
Yeah, it'd be quite an interesting purchase, wouldn't it? I want an aviation quality GPS to tell me where I am to the nearest few centimeters. Why? Yeah. Right. Okay. If there's no more questions, I think we've lost Phil anyway. I can just see a chair, so I'll go back to my presentation, and we can. Right. So let's. Right, so I'm going to talk about now. So far, I've focused on GPS, And as I talked about earlier on in the talk, then of course GPS is now no longer the only sat-nav system. So I'm going to talk about some of the other ones. Now, one you may be familiar with is GLONASS. Towards the end of the Cold War, the Soviet Union developed its own version of GPS, and it's, in the English language at least, it's called GLONASS, which is an abbreviation for Global Navigation Satellite System. And like the American system, it was for military use only. But GLONASS wasn't completed by the Russian government until 1995. And that was actually 4 years after the breakup of the Soviet Union, the end of the Cold War. And the satellites only had a lifetime of 7 years. And in the 1990s, as many of you may know, there was an economic crisis in Russia. So almost as soon as it was finished, the satellites began to fail, and there just wasn't enough money to replace them. So by the end of 2001, there were actually only 6 working satellites, and you need 24 to give full coverage of the Earth. So in the year 2000, we got to the stage where, yeah, I mean, it was almost unusable. But then the Russian economy improved and the funding to re-establish the service became available. And the Russian government made the commitment that, like GPS, it would be a civilian service, freely available to civilian users all over the world. And in 2015, the system became fully operational again, with 24 satellites covering the globe. But even before then, many smartphones had multi-satellite chips which can receive both GPS and GLONASS signals. And this provides greater accuracy because the phone can't lock onto a strong signal from GPS. It can supplement this with signals from the GLONASS satellites. But the big one, I'm sure you've all heard of, is Galileo. And I'll say current estimates would say probably 6, 7, maybe as much as 10% of the EU's GDP depends on sat-nav applications. And this includes critical sectors such as energy, telecommunications, and even financial services. And if sat-nav services were in Europe to be disrupted for even a few days, the large-scale economic losses would be massive. So to address this, the EU announced back in 2002 that it would build its own sat-nav system, and it was called Galileo, obviously after the Italian astronomer. And this was somewhat ambitiously expected to be fully up and running by 2008 at a cost of 3 billion euros. But as I'm sure you know, that didn't happen. There were numerous delays, and the cost has ended up being 3 or 4 times the original cost. Currently, we're pretty much there. There are 22 Galileo satellites up and running, with a couple more to go up, I think, by 2023. But the thing about Galileo is GLONASS and GPS are both military, or they have origins in military programs. And to some extent, they're both under military control. Whereas Galileo is a peaceful collaboration between the individual member states of Europe, and it's always been firmly under civilian control. It's never had anything to do with military operations. And interestingly, to encourage its use, from 2021, all new smartphones sold in the EU must have chips which can receive Galileo signals. And you can go on a website, use Galileo EU, and check that your phone is Galileo compatible. And I'm an iPhone user, and I found mine. It's not bang up to date. I've got an iPhone XR, and that's fully Galileo compatible. I'm not sure this list is right, actually, because the new iPhone SE isn't on this list, which I think is probably a mistake. And you recall I mentioned there were 4 systems. The 4th is, of course, Beidou, the Chinese system, which since 2018 has provided a global sat-nav service. So, okay, we've talked about the systems which are up and running now. I'm going to talk about other countries which might go into the market. I'm going to focus on the UK and India, because of course, since we've left the EU, there was a talk at one stage about British Global Navigation Satellite System, BGNSS, and I'm surprised it didn't provide a more snappy acronym for this. And this was considered, but I think it's fair to say it's been scrapped at the moment. It's not going to progress, partly because it's going to cost a lot of money. You're talking probably, you know, realistically, probably about £10 billion, that sort of amount of money. And with the crisis due to COVID, there's probably not the money, or arguably even the need to build such a system. But the other country I'm going to talk about is India. India has an interesting sat-nav system. It's called a regional sat-nav system, which they use. It's a little bit different from the other systems because it actually uses geosynchronous satellites. So these provide a sat-nav system, but only over India and a region 1,500 kilometers around it. So you only need 7 satellites, but because you're not covering the whole world. And they've got another 2 satellites on the ground which could be launched if the ones failed. So what I want to do now, I'm just going to stop sharing because there's a little thing I want to show you, which was quite interesting. So I'm going to share my screen again. Can you all see this?
Yeah.
Yeah. So this is just showing you the various satellites of orbit. So if we look, there's various ways of using this. I mean, one is let's just go here and show them all. So you've got let's say here you've got the blue line, purplish line, which is GPS. Then just outside that you've got Beidou, orange one. Then you've got Galileo, which is the green one. So we'll focus on. Let's say you've got GPS, Beidou, Galileo, GLONASS, and these are all in the Middle Earth orbit. So it takes roughly 12 hours to go around the Earth. They're all very slightly differences. And I've also in this Mars orbiter, you've also got the geostationary orbit here, where it takes exactly 23 hours, 56 minutes to go around the Earth. And there is something called the graveyard orbit, you'll see. And what this is because the geostationary orbit is so packed, when a satellite has finished its operational lifetime and it's a geostationary orbit, you can't deorbit it like you can with a low Earth orbit satellite. So it would come and do re-entry. It would take too much energy to do that. So what they do with geostationary orbits is they should raise them about 300 kilometers, switch off all the electronics, and the satellite just sits there. So it's not in any danger of colliding with something in a geostationary orbit. So what I'm going to do now is I'm going to pause and ask anymore. Does anybody have any questions at this point?
Can I just ask something?
Yeah.
When you get these websites that show you all the satellites in orbit, there are literally hundreds.
Yes.
So when they're not part of the GPS system or geostationary Earth orbit, what are all these other bits of stuff going around?
Right. Okay. Yeah. I mean, there are lots of satellites in. I've seen those diagrams. I perhaps should have.
They're amazing. It's like
yeah. I mean, they are amazing. The other thing is this diagram is 2-dimensional. It's not quite right because these satellites aren't all orbiting in the same plane.
Right.
You know, they're on different planes. But yeah, I mean, there are a lot of, you know, all TV satellites, you know, will be in a geostationary orbit. A lot of communication satellites are in a geostationary orbit. The big one is the geostationary orbit, where the plane is at the equator and the orbital period is exactly the same as the Earth's rotation. So if you look at those, there's a big spike there. The biggie is going to be satellite broadband, because at the end of 2019, there were 2,000 active satellites in orbit, and there's probably about 5,000 satellite defunct ones. But the big one is going to be these massive broadband satellite constellations, where Elon Musk's SpaceX, they've got launches of 60 satellites at a time. They're just going to be pumping those up for the next years, and that's going to be fast internet broadband, and those are all going to be low Earth satellite, and that's why astronomers get upset about them, because of course they're closer to the Earth and brighter, and that's going to be a completely game changer, because we had 2,000 satellites in orbit at the end of 2019. SpaceX have permission to launch 12,500 satellites by the end of middle of the decade. You know, it's incredible. And then there are other operators as well in this thing. There's Amazon, OneWeb, Telesat, I think. So I think that's going to be the big thing, satellite broadband.
We did hear that SpaceX were going to put sunshades on their satellites to save reflecting back to the Earth.
Yeah, I mean, they are doing that, and it reduces the brightness. They did have one called DarkSat, where they painted it dark to see what the effect was, but that was beginning of last year, but it didn't, nothing much was heard about that. And I was digging around while researching for another talk, and they said they had problems with the thermal stability of the satellite when it was covered in a dark coating. So that idea was abandoned.
Steve, you said he was given permission. Sorry, it's Francis here. Who gives permission?
Yeah, that's a really interesting question.
How do they get worldwide agreement?
Yeah,
they don't.
Who owns that? That's a whole interesting debate, that, isn't it? You know, who owns the skies? You know, who? Now, I'm not an expert on this, but there is a lot of debate around that. Who owns this? I mean, I think there is the International Telegraph Union. No, I don't know, Tom, are you on the call? You know, with your sort of like, do you know? Would you be able to add anything to that?
I'm not sure who's doing it. One talk we had recently said they don't need permission because nobody owns the sky.
Yes.
So there's no UN body.
Yeah.
The ITU don't have jurisdiction as such. They talk about frequencies, but not orbits. So I'm not sure it's covered.
I mean, what I've heard one person say is that Elon Musk SpaceX will just keep launching them until somebody tells them to stop. You know, it's and I'm not sure who would tell them to stop. What is clear is that optical astronomers don't have a monopoly. So if, you know, the worst case scenario, the night sky was completely ruined, but you had fast internet broadband to all corners of the world, then some people might well say, yeah, that's a trade-off worth paying. You know, it's not.
But this amount of tech up there is actually a security issue as well. I mean, as soon as you put a satellite up, so, and of course the US ones are a challenge to China, or the Chinese ones are a challenge to. I can't see this continuing without some sort of showdown at some time.
Space is getting very crowded, and what's happening with the broadband, satellite broadband, it's a complete game changer in terms of volume of stuff you're putting up there. You know, it's totally different from anything that's happened so far, just in terms of quantity of satellites.
Will the broadband satellites interfere with the GPS ones?
Well, I mean, as I understand it, there'll be different frequencies, and of course, you know, they're completely different orbits. And the GPS ones are middle Earth orbits. The broadband ones have to be close to Earth because you need a much stronger signal, because you've got like a two-way communication. Not sure. I'm assuming the answer to that question is no. But one thing interesting I did read a while ago is that when the first satellite Sputnik 1 was launched, there was an interesting debate about whether, because of course it flew over lots of countries of the world, but at a very high altitude. You know, obviously, if you're in a plane, you need permission to go over Soviet airspace. But whether Sputnik was flying over other countries, whether it needed permission, and I think when, you know, obviously it didn't get permission, and that sort of set a precedent, really, I suppose, that you didn't. Yeah, I mean, pretty much, I think it seems to be a sort of free for all, really. I mean, it's unclear who owns space, if anybody. It's an interesting question.
As a point of interest and relevance, in my hand I've got the second GPS I ever bought, which
Right.
was for walking and being out in the hills, and it's showing me this. I'll turn that light off. Can you see? It's showing the satellites it can see at the moment.
Yeah, it's telling you the ones it's connected to. Yeah.
And I've been watching it during the course of the last 10 minutes or so, and it changes.
Yes. Yeah, it will lock onto different ones. Yeah.
It's locked on to about 9 satellites at the moment, but they are changing as we talk.
Yeah. And you only need a good signal from 4 to get position. So yeah.
And it's telling me my accuracy location is accurate to plus or minus 13 feet.
That's pretty good. Yeah. Yep. Mm.
It's not as handy as my phone.
No. Okay. Well, shall I go on to the next session, because we've got time for questions at the end. So I'll stop sharing, and then I'll go on to the next part of the presentation. Okay, so where are we? Let's have a look. Okay. Right. Right. Can you all see that?
Yes, we can.
Yeah.
Yes.
Right. Brilliant. Okay. Right. So we'll continue from the current slide. Oops. Right. So I'm going to talk now about jamming GPS. And this is an activity which I think may come into more. Let's try and get rid of these people. That's better. Right. Okay. I mean, the first thing to think about is that GPS signals, and we already talked about this, are very weak. And this is because the typical power of a GPS satellite is about 0.5 kilowatts, similar to that from a mobile phone mast. However, a GPS satellite is at least 20,000 kilometers away from the receiver on the Earth's surface. So as you can see in the diagram below, by the time it reaches the Earth's surface, the signal is spread out over such a large area that's extremely weak, and is typically measured in picowatts. That's 10 to the minus 12 watts per square meter. So let's do a quick back of the envelope calculation. I'm going to make some assumptions. Satellite transmitting at 500 watts, 20,200 kilometers away. And I'm going to assume that the signal is evenly distributed. It's not, because any signal will be stronger in the center of the beam and weaker as you go out. But let's assume that's evenly spread out for the calculation. So it spreads out over 100 million square kilometers, okay, from this distance. So that's 10 to the 14 square meters. So the intensity, which is just power per unit area of the signal, is 500 divided by 10 to the 14 watts per square meter. So it comes out as 5 times 10 to the minus 12 watts per square meter. 5 picowatts. That's a very weak signal. And then let's assume that we've got a receiver which has an area of, let's say, 10 square centimeters, right? So that's actually slightly wrong. Yeah, that's right. Yeah, okay, got it. Right. So that's what the intensity. That's the intensity. That's the area. So the power received by a receiver having an area of 10 square centimeters is 5 times 10 to the minus 15 watts. So that's pretty weak. Right. So the obvious conclusion is that it doesn't take much power to jam sat-nav signals. And if a signal were, someone were to transmit on the same frequencies used by GPS satellites, it would have to be a very small fraction of a watt to block out or jam the signals over a large area. And if GPS signals were jammed, then it could be quite severe, because sat-nav systems, and not just for individual, for military emergency services, wouldn't work. GPS tracking devices wouldn't work. And it's possible even the aircraft wouldn't know their position. So who'd want to do this? Well, it could be a number of people. It could be just individuals wanting to protect their privacy. It could just be someone driving a lorry, and they might want to not to know their employer knowing where they were. Be criminals, car thieves wanting to steal cars and not be picked up by the tracker, organized criminal gangs, terrorists, or even hostile states as an act of war. And it's not only jamming, it's possible to spoof sat-nav signals. So what you do is you send out a frequency, send out a signal on a GPS frequency, but with different position information. So this completely confuses the receiver. We can think it's in a different place. And there's evidence that Iran has done this at spoof some American unmanned aircraft to confuse them and misdirect them to go to the wrong place. And here's some examples of state-sanctioned jamming. There's evidence that the Russians use this to disorientate a UAV. So that's an unmanned aerial vehicle, which was doing it as peacekeeping on a special monitoring mission to Ukraine. And there's evidence that the GPS signals were jammed and the aircraft became disorientated. Russia uses jamming quite widely in military exercises, and countries bordering Russia have been repeatedly subjected to jam in Russian military exercises. And there's this evidence here that there've been some trouble with airliners potentially getting lost, which could have severe implications. And there's other countries which have experienced trouble with Russian jamming. And China has reportedly used this against its neighbors to try and confuse military operations. And interestingly, I found out our own Ministry of Defence occasionally carries out sat-nav jamming facilities. And these are carried out for short periods of time, typically in very remote areas. But even so, because the GPS signals are so weak, people using GPS on the sat-nav in the car can be affected by these. And if you go on the Ofcom website, navigate to GPS jamming exercises, you'll find there are a few of these. South Uist, if you know, is an island in the Outer Hebrides. It's quite a remote area. I mean, they wouldn't do these in a populated area. And this is really interesting. You can actually buy over the internet GPS pocket jammers, and this device here is advertised. So you can hide the location of your car if you suspect it's being equipped with a GPS tracking device, because those are the two main frequencies used by GPS, L1 and L2, which I've talked about earlier. And looking at the spec of this device is extraordinary. I mean, I looked at its size, 64 by 37 centimeters. So this is actually smaller than a credit card. And the weight of it, excluding the battery, is 34 grams. And its weak transmitter, it's only going to be power of milliwatts, but it's still going to be sufficient to knock out GPS signals over quite a large area. And really interestingly, in the UK, it isn't actually illegal to buy such devices. In fact, I found this over the internet when I was researching this talk, but it is illegal to use them. So it's a funny sort of grey area. And there was a fascinating case where somebody was using this, the London Stock Exchange, and people's GPSs in their cars stopped working, and the timestamps in some financial trades were affected as well. And it was a delivery driver hiding from his management. Fascinating. So finally, on a final note, you know, you could argue all this dated from a change of policy by Bill Clinton, who made a change, stopped selective availability, kick-started a whole GPS industry. But would GPS been available if the previous president had been in charge? The answer is probably not. So I'm going to stop sharing now and ask if there's any more questions.
Steve, that was tremendous. Thank you. I think leave it open forum. I think there was one or two questions. Andy Hewitt, you wanted to ask about numbers of GP satellites. How many would be too many?
I think it was picked up on the next slide, Phil.
Okay.
Just as I asked it, he put he shared his screen, and it showed that they were in different orbits. So
yeah,
it kind of counteracts my question, if you like.
Yeah, I mean, GPS, there's 6 orbital planes with 4 satellites in each. Yeah.
Cheers.
I think you've delivered a talk on a topic that is we all unwittingly or knowingly use and rely on, and it's and I think with the little credit card jammer to larger scale jamming, we're all very vulnerable to it.
I was just thinking it's made me feel very vulnerable.
It is. I mean, it's extraordinary that you can. I logged on and I found this device. I thought surely that's illegal but no, you can buy it. It's illegal to use it, but it's not illegal to buy it, which is very strange.
Steve, your generation and my generation will be okay because we know how to read maps.
Yes, but oh yeah, I mean, my niece, who's only 35, when I had an old atlas, and she said, I said, you want a paper map, as if I'd asked her for a sort of a stone tablet or something. A paper map, what's that? Yeah, but yeah, it's interesting. It's very interesting, and I find it quite interesting that the sort of symmetry, because the whole thing arguably started with the downing of that Korean aircraft, which has strayed onto Soviet airspace. And now 40 years later, probably Russia is the country that's doing the most GPS jamming in military exercises than any other country. So there's a sort of weird sort of symmetry about it.
At the scale that
it does make you wonder if some of the aircraft that have gone missing, whether there was a jamming thing involved with that. The Malaysian aircraft. And that you wonder if something happened there. Anyway. More an observation than a question.
Yeah.
Phil, sorry, Steve, at the scale at which the Russians
jamming, will they have aerials? Is it done? Until I saw the little credit card thing, I'd assumed that jamming of GPS was done by other satellites. It wasn't based terrestrially.
I don't know, to be honest. I mean, I think we can only. I mean, I don't know. But the thing to point is, it doesn't. You know, if you've got, it doesn't take much, because the GPS signals is quite astonishingly weak by the time they hit. Just because of the inverse square law, it doesn't take much power to.
Yeah. Can I ask a couple of questions, quick ones? One's a silly one. You mentioned the different countries' orbital systems, and you mentioned a Middle Earth orbit.
Yeah.
And I've been looking up Middle Earth in here.
Oh.
I can't find their system in here for more.
The moment you said Middle Earth, I knew what you were going to follow it with.
I knew you. Yeah.
All right, sorry, but a serious question was more technical one. Is the GPS that we do use every day? And Phil, by the way, it's so encouraging to see that you've set up your laptop with your maps in the top left-hand of the screen there, the orange.
Yep, orange and pink.
Good stuff. So just how does it work with a smartphone that's getting the GPS signals? How does it, I don't actually drive, so I don't have a TomTom or anything like that. But how does the mapping, how does it show me when I go onto Google Maps or even Apple Maps on this? How does it do that? How does that work?
Well, I mean, I can answer the question but I'm sure there's other people who can add to it. I mean, basically, you need two things to find your way about. You need to know where you are in terms of latitude, longitude, and then you need some mapping system which will overlay that onto a physical map of the Earth. And that's what Google Maps is, isn't it? It gives you an overlay of the two. I don't know if anybody wants to add something to that, or
so just to get it right, if I think I've got it, the GPS signal, so that the phone kind of knows where it is in some sort.
Yeah. The phone uses the GPS satellites to get basically X, Y, and Z coordinates, and as a byproduct, a GPS receiver will also give you a very accurate time as well, coordinated with the atomic clocks, because that's the other thing it needs as a byproduct. And you only need 4 satellites to give you that.
Phil, I think you were going to explain as well.
Because you've appreciated my Ordnance Survey maps in the background. I've got the Ordnance Survey map on my phone.
Oh yeah.
And that red dot tells me where I am. But I'm sure that's not so lot of a surprise to many people. Steve, something I've heard is that GPS is less accurate for elevation positioning than X and Y horizontal positioning. Is that true?
Well, I don't know, because off the top of my head, I don't pretend to be I couldn't necessarily see any reason why that should be the case.
Right.
But I'm not. I wouldn't pretend to be an expert in this.
Have you heard that, or am I making?
Well, I've heard that as well, but I was trying to think why. Because basically, you're solving 4 equations to give you X, Y, Z coordinates and a time. So why it should be less accurate? I mean, what? Yeah. I don't know, to be honest. I don't know.
Can I ask a question about the jamming again, please, Steve?
Yes.
Are GPS satellites safe from a big global terrorist jamming attack on a large scale by the very nature of their usefulness. I.e., if they jammed the satellites, then the terrorists jamming them wouldn't then have use of them as well. Does that make sense?
Oh yeah, yeah. I mean, it does. I mean, you could, if you were an organized terrorist cell, you could put transmitters all the way around the world, which transmitted on GPS frequencies, and wipe out the entire GPS network, and do that for the other things. But that would take out with organization. You need to have these transmitters all over the world. You could do it in a particular region. You could wipe out, you could no, if you take an example, if you want, you could say, let's take London. Let's put a big transmitter. It would have to be fairly high up because of line of sight, but we go to the top of telecom tower and put transmitter transmitting on all these frequencies of all satellites. You could knock out everything, so people in London couldn't use sat nav.
I'm just curious to know why there hasn't been an attack of that kind, because it seems like it's quite.
It would take a lot. It would take a lot of organising.
You'd also, Andy, it's Kevin. You'd also need a lot of power to override the signals, and the signals intelligence would be able to pinpoint the transmission location through triangulation.
I'm not considering it. It's not an avenue I'm looking at.
It was one of the. I think everybody asks those kind of questions. So it sounds easy on paper. In practice, it's a lot harder. So if you think about pirate radio stations, you don't tend to get many of those, but they're essentially using a small version of a big jammer. But if you had a wideband transmitter, you could locally knock out a lot of the telecoms quite quickly.
Yeah, I mean, the only thing I would add to that, Kevin, is you wouldn't have to be that powerful, because GPS signals are very weak by definition, because the transmitter is so far away. So I'm not sure how much you'd need in terms of power. I mean,
it depends on your area of coverage.
Yeah.
So if you like I said, if you wanted to knock it out for the centre of Manchester, you just need to go up one of the tall towers, plug it into the mains, and you'd be off the races.
But you'd have to transmit on frequency, because GPS uses 3 frequencies: L1, L2, L5. Galileo uses different frequencies. GLONASS use different frequencies. You'd have to transmit on all of these frequencies, or have something very sort of.
And that's where, if you did knock out GPS, you'd simply flip to Galileo, or you'd flip to Cosmos.
Yeah, so you'd have to knock out all of those frequencies.
Knock them all out simultaneously to really do some damage. So it's largely quite impractical, and also getting your hands on particular equipment that will do broad spectrum jamming is actually a lot more tricky than it sounds. So you can homebrew things, as I found out from my cost.
It sounds like we're quite safe from it, which is good to know.
I think the interesting thing, sorry, Steve, that
right.
example you gave of the delivery driver.
Yeah.
One of the impacts was wrong timestamps on trades from the stock exchange.
Yes.
Or if you could reliably do that, you could interfere with financial transactions.
You could do, couldn't you? Yeah. If they're using, because a lot of systems use GPS to get. By using GPS for time signals, you're getting a time accurate to the best atomic clocks as a byproduct. Yeah. So
a lot of telecommunication centers, mobile phone masts, use GPS signals for their timing. So if you're going to attack and you knock GPS out, it has a lot of knock-on effects, as well as just not finding out where you are.
Can I flag up the flag for some peaceful uses of GPS? Because I do need to sleep tonight, not have nightmares of things. I remembered that they've done fantastic things where they've put devices on migrating birds, and can track them, which is utterly phenomenal, you know. And then if say like it's the season for the swallows to be arriving in the UK, and when there's concerns about birds not arriving, you can see where perhaps situations in other countries through climate change or even mass shootings, birds and all that.
Yeah, I mean,
I think they've put them on turtles as well, haven't they? All sorts of animals have got them on.
Yeah.
They're very cheap now. I mean, I find it funny. You can GPS your kids with a little sort of thing on the back to exactly where they are, and I think they do that a lot, particularly in the States. You know, kids, probably a good percentage of middle-class kids have a GPS tracker attached to them.
They're surgically inserted, I think. Maybe it might be part of wedding ceremonies. Oh gosh.
Prenuptial contract.
Let me mute myself.
I think, Steve, we're getting to the end of the talk.
Yeah. Okay, all right.
Does anyone else have any further questions they want to ask of Steve before we start moving to saying thank you and good night?
Okay. One more last ones. What about being how are those satellites, because they're so important in every facet of life these days? Are they specially hardened against, say, coronal? You know, the coronal mass ejections that are always a possibility of.
Right. I mean, all I know when doing is they've got a lifetime plan of about, I think it's 12 to 15 years, the modern GPS satellites. So beyond that, I don't know. They'll be hardened to some extent. I don't know if anybody else knows any more than that, but I think
don't they shut them down if there's if they think there's going to be a big flare or a lot
of
I believe so.
Okay, I'd like to, Steve, that was a fantastic talk.
Thank you.
You captured the imagination, the interest of us all, and it's something that we all use, we all take for granted. I've over the years, I've sat and thought and wondered about how GPS systems work, but you've certainly answered a lot of my curiosities, my interests, my questions, and I think that it's fair to say that applies for many people here. So I just say thank you very, very much for your talk, for the interest, as you have done for us many times before, and particularly thank you for putting this together in such a hurry and bailing us out again.
It's all right.
Yeah, I endorse that. You've been wonderful, because I have to find another speaker at short notice. It's not.
Oh well, I'll make sure that I don't go on holiday in times of. Did you say September? You might be struggling.
Oh, we'll be all right by then. But we have lent on you. I think this might be. I think we've lent on you a number of times before, and you've always risen to the challenge. And
thank you.
And I've enormously enjoyed this evening, and so thank you very much, very, very much for that.
Can I just ask one question? I know I've come in late here, but you did mention that with the satellites, they become, after a space of time, then obviously they become obsolete and they just are switched off and they sort of just orbit in the space or stay in that sort of zone. I mean, over time, the more and more that there's going to be obsolete ones there. How are they going to get them down? Because you're just going to clutter up that area for more ones to go up there, aren't you?
Well, yeah. I mean, the problem is low Earth orbit satellites will decay gradually. And if you take example of the International Space Station, its decay rate is, I think it's about 2 kilometers a year at 400, and it needs to be raised every so often. So if you leave a low Earth or satellite, it will gradually spiral back. What they do with low Earth or satellites now is they deorbit them, so they deliberately slow them down so they drop back to Earth. Now that's not possible with something like a geostationary satellite. It would take a lot of energy to slow that down, to bring it. So what they do then is they just, what they used to do is just switch it off and leave it there, and it just stays there forever. What happens now is they move it to a graveyard orbit. So that's not because the geostationary orbit is the important slot. So it's not hogging a slot in a geostationary orbit. So lift it up about 300 kilometers out of geostationary, and essentially it just sits there with all its systems switched off. Potentially, you know, at that height, it will remain there for millions of years because the decay rate is slow, so slow. There's nothing to bring it back. So eventually, yes, I mean the graveyard slot will gradually fill up over time. But
can you give me some idea how they compute the orbit of rockets or shuttles through all this mass of satellites? I mean, I know the space station is low, isn't it? But when they start going to planets, to the moon, I mean,
well, it's just
through this stuff.
Well, what do you mean? Well, I suppose they've got to know what you're saying. Are you saying that?
Well,
what's to stop a space mission hitting a piece of space junk? I suppose.
Exactly. Yeah. I mean, a very, very small piece of metal can produce tremendous damage.
And of course, that wasn't a problem because everything since 1972, the end of the Apollo missions, has been low Earth orbit. So we've not gone outside low Earth orbits, and the Apollo missions, it wasn't an issue because there wasn't stuff. I'm not sure. I mean, I understand the space junk is quite well plotted, the bigger bits of it, but
when they're talking about shooting it down or something, or trying to.
Well, yeah, but you can't get everything down, the smaller bits,
and hoovering it up. I've heard
hoovering it up. Yeah, I've heard.
Yeah.
Maybe it's a subject for a topic for a talk for someone to do, space junk.
Be good.
Okay, it's time to. I think we've taken enough of your time, Steve.
It's all right.
Just before we go, I wanted to say, beyond saying thanks, Steve, which I've said, and I think everyone would agree, and there's nothing else. Not to say there's nothing else to say, but I wanted to mention one or two other things.